Tonight, we're going to drift through one of the most fascinating subjects in astronomy, something both intimidating and strangely beautiful, something that hides in the darkness yet shapes entire galaxies. We're going to spend some quiet time with black holes. Now, that phrase can sound dramatic at first. Black holes have a reputation after all. They're often described as cosmic monsters, devourers of stars, bottomless pits in space where even light cannot escape. Films and documentaries like to show them as roaring whirlpools or glowing maws tearing apart anything that comes close. But the real universe is usually calmer than that. Vast, quiet, patient. And black holes, for all their power, are part of that quiet universe too. So rather than imagining something violent or frightening, it may help to picture black holes as deep wells in the fabric of space, still and silent, shaping everything around them in ways that are subtle most of the time, and dramatic only under certain conditions. They are not cosmic vacuum cleaners sweeping up everything nearby. In fact, most black holes spend the majority of their existence doing very little at all, simply sitting in the darkness, surrounded by stars that orbit peacefully at safe distances. Before we go any further, I'd like to ask you something gently. The same way one might ask while sitting beside a window at night. Where are you listening from right now? Perhaps you're in your bedroom, the lights low, the world outside quiet. Maybe you're travelling, listening through headphones while the hum of a train or the soft noise of distant traffic drifts in the background. Or maybe it's late afternoon where you are, and this is simply a moment of rest in a busy day. And one more small fitting question, what time is it for you right now? It's interesting, isn't it, that we can be scattered across continents, across time zones, across entire hemispheres, and yet meet here in the same quiet moment, thinking about the same distant objects that lie far beyond all of us. If you find this kind of slow exploration soothing, if it helps your thoughts settle or simply gives your mind something gentle to follow, I'd be grateful if you gave the video a like and perhaps subscribed. It helps this calm corner of science reach more people who might need a peaceful place to rest their thoughts for a while. Now, let's begin easing into the story. Black holes are among the strangest objects ever discovered, but in a way, their story begins with something very familiar: gravity. Gravity is the reason your feet stay on the ground, the reason the moon circles Earth, the reason planets follow their paths around the sun. It's the quiet force that shapes the large-scale structure of the universe, working constantly, invisibly, without hurry. Usually gravity is gentle when you notice it in daily life. A falling leaf, a dropped cup, the weight of a blanket. But gravity has no real upper limit. If enough mass gathers in one place, gravity becomes stronger and stronger, bending space itself more and more. That idea alone is already remarkable, that space is not just empty nothingness, but something that can stretch and curve like a flexible surface. Massive objects like stars and planets create gentle dips in that surface. Black holes are what happen when the dip becomes so deep that it forms a kind of well, with sides so steep that nothing inside can climb back out. It's worth pausing here and letting that idea settle for a moment, because it's easy to rush past it. A region of space where escape is impossible, not because of walls or barriers, but because the structure of space itself is curved so intensely that every possible path leads inward. And yet, even that description can make black holes sound more dramatic than they usually are. From far away, a black hole doesn't look like a spinning vortex or a glowing eye. If it isn't actively pulling in gas or dust, it can be almost invisible, detectable only by the motion of stars around it, or by subtle gravitational effects. In fact, if our sun were magically replaced by a black hole of the same mass, something interesting would happen. Earth would continue orbiting almost exactly as it does now, The seasons would vanish, of course, because there would be no sunlight, and that would be a serious inconvenience, but the orbit itself would remain stable. Gravity depends on mass, not on whether that mass is shining or dark. So black holes are not defined by some kind of cosmic hunger. They are defined by density, by matter compressed into an incredibly small volume, creating gravity so strong that the escape velocity exceeds the speed of light. That phrase, escape velocity, is simply the speed needed to break free from gravity. On Earth, rockets must reach about 11 kilometers per second to escape our planet's pull. That's fast, but still achievable with enough fuel and engineering. For a black hole, the escape velocity exceeds 300,000 kilometers per second, the speed of light itself, and since nothing can travel faster than light, nothing that crosses a certain boundary can ever return. That boundary is called the event horizon, a name that sounds technical but has a simple meaning. It's the point beyond which events cannot affect the outside universe. Anything that happens inside remains hidden forever. It's a quiet boundary. There's no flashing line in space, no sudden jolt as you cross it. If you could somehow approach a black hole safely, you wouldn't see a glowing barrier. You would simply pass a point of no return without noticing anything special at that exact moment. There's something strangely peaceful about that idea. The universe, even at its most extreme, doesn't always announce itself with drama. Sometimes the most profound boundaries are silent ones. Over the years, astronomers have discovered that black holes are not all the same. There isn't just one kind. Instead, the universe contains a whole family of black holes, ranging from ones only a few times the mass of our Sun to giants billions of times more massive, lurking at the centers of galaxies. Some formed from dying stars. Others may have formed in the earliest moments of the universe, long before galaxies existed. Some drift alone through interstellar space, while others exist in pairs, orbiting each other in slow spirals that eventually end in powerful collisions sending ripples through space itself. And that's really what makes this subject so fascinating. When we talk about black holes, we're not talking about a single phenomenon, but about many different kinds, each with its own origin, behavior, and role in the cosmos. It's a bit like talking about oceans. At first, you might think of one vast body of water, but then you realize there are shallow seas, deep trenches, coral reefs, and currents that circle the globe. Black holes, in their own way, form a landscape just as varied. For most of human history, black holes were purely theoretical. The idea began as a mathematical curiosity. In the 18th century, long before modern physics, a few thinkers wondered whether gravity could ever become strong enough to trap light. At the time, light was thought of as tiny particles, and the question seemed almost philosophical. Then, in the early 20th century, Einstein's theory of general relativity changed everything. Gravity was no longer just a force pulling objects together, it was a curvature of space and time themselves. And within Einstein's equations, there were solutions that described regions where that curvature became extreme. At first, even Einstein himself was skeptical that such objects could exist in reality. The equations allowed them, but nature often has a way of avoiding the most extreme possibilities. For decades, black holes, as real physical objects, remained uncertain, more like mathematical shadows than astrophysical realities. It wasn't until the mid-20th century that evidence began to accumulate. Astronomers started detecting invisible companions to stars, objects that exerted strong gravitational pulls but emitted no light. Later, powerful radio and X-ray telescopes revealed energetic regions at the centers of distant galaxies, far too bright to be explained by ordinary stars. Gradually the picture became clear. Black holes were not rare curiosities. They were common features of the universe. And yet, despite everything we've learned, black holes still carry an air of mystery, not because we understand nothing about them, but because they sit at the boundary of several great areas of physics. Gravity, quantum mechanics, thermodynamics, and the nature of space and time itself all meet at the edge of a black hole. That boundary between the known and the unknown has always been a place that draws human curiosity. We're naturally interested in edges, horizons, limits, the points where understanding fades into speculation. But tonight, there's no need to rush toward the deepest mysteries all at once. Instead, we can take our time, moving gradually, beginning with the simplest and most familiar kinds of black holes, the ones formed when massive stars reach the ends of their lives. Before we get there, though, it's worth pausing for a moment to appreciate how remarkable it is that we can even know about these objects at all. Black holes emit no light. They are, by definition, dark. And yet, through careful observation, patient measurement, and a great deal of imagination, scientists have learned to detect them, weigh them, even photograph the glowing matter swirling around them. That first image of a black hole, released in 2019, was not a photograph in the usual sense. It was a reconstruction based on data from a network of radio telescopes spread across the Earth, working together like a single instrument the size of our planet. The result was a faint ring of light surrounding a dark centre, the shadow of a black hole against the glowing gas around it. It's a quiet image, almost understated, but it represents decades of effort and centuries of curiosity. And perhaps that's one of the most comforting things about science. Even the darkest, most distant objects can be understood, little by little, by minds that are patient enough to ask careful questions and wait for careful answers. Each type tells a different part of the same story. A story about gravity, matter, and the long history of the cosmos itself. To understand the many kinds of black holes that exist, it helps to slow down for a moment and look carefully at what a black hole actually is, in the simplest possible sense. The term itself can feel heavy with mystery, but at its core the idea is surprisingly straightforward. A black hole is a region of space where gravity has become so strong that nothing, not even light, can escape once it crosses a certain boundary. That boundary, as we briefly touched on earlier, is called the event horizon. It isn't a surface in the usual sense. There's no solid shell there, no barrier you could tap with your hand. Instead, it's more like an invisible threshold in space. Outside it, escape is possible. Inside it, every possible path leads inward. What makes this especially interesting is that a black hole isn't really an object in the way a planet or a star is. It's more accurate to think of it as a condition of space itself. When enough mass is squeezed into a small enough volume, gravity becomes overwhelming, bending space and time so steeply that all roads lead toward the centre. That centre is often called the singularity, a word that sounds technical, but simply refers to a point where our current understanding of physics breaks down. The equations predict that matter is compressed to an extremely small region of enormous density, but what truly happens there is still uncertain. Scientists suspect that a complete theory of quantum gravity, something we don't yet have, will be needed to fully understand it. Fortunately, for our purposes, we don't need to peer all the way into that deepest mystery. Much of what makes black holes fascinating can be understood by looking at the region around them, where gravity shapes the motion of light and matter in ways that are dramatic but still describable. One of the most helpful ways to picture this is to imagine space as something flexible rather than rigid. This isn't just a metaphor. In Einstein's theory of general relativity, space and time form a single fabric that can curve. Massive objects like stars create gentle curves in that fabric, and planets follow those curves, which is what we perceive as gravity. A black hole is what happens when that curvature becomes extreme, forming a kind of funnel so deep that the slope becomes effectively vertical at the event horizon. Beyond that point, every possible direction leads downward. It's worth noting something that often surprises people. A black hole doesn't actively suck things in from vast distances. If you were far enough away, you could orbit a black hole just as safely as you orbit a star of the same mass. Gravity depends on mass and distance, not on whether the object is a black hole or a shining star. This means that many black holes are not surrounded by swirling disks of glowing gas. Those dramatic scenes you sometimes see in visualizations occur only when a black hole is actively feeding, pulling in nearby matter that heats up as it spirals inward. In many cases, black holes exist quietly, with little happening around them at all. Another idea that helps build an intuitive understanding is escape velocity. Every object with gravity has one. It's simply the speed you would need to leave that object's gravitational pull without further propulsion. On Earth, that speed is about 11 kilometers per second. On a neutron star, which is already an incredibly dense stellar remnant, the escape velocity can be a significant fraction of the speed of light. For a black hole, the escape velocity at the event horizon exceeds the speed of light itself, and since light is the fastest thing that can travel through space, nothing inside that boundary can ever climb back out. Interestingly, the event horizon itself doesn't mark a place where gravity suddenly becomes infinite, or where conditions instantly become destructive. If you are falling toward a very large black hole, you might cross the event horizon without noticing anything unusual at that precise moment. The real dangers, such as intense tidal forces, depend on the size of the black hole. Smaller black holes have stronger tidal forces near the horizon, while larger ones can have relatively gentle conditions there, at least temporarily. Tidal forces are another concept worth understanding, because they play an important role in what happens near black holes. Gravity becomes stronger the closer you get to a massive object, and if the difference in gravitational pull between one part of an object and another becomes large enough, it can stretch that object. Near some black holes, this stretching effect becomes extreme, a process sometimes called spaghettification, which is exactly as descriptive as it sounds. The difference in gravitational pull between your feet and your head could become so large that you would be stretched into a long, thin shape. It's not a pleasant thought, but it's a good illustration of how gravity behaves in extreme environments. Fortunately, these effects occur only very close to the black hole. At safe distances, gravity behaves in a perfectly ordinary way, following the same laws that govern the motion of planets and moons. Light itself behaves in fascinating ways near a black hole. Because gravity curves space and time, it also bends the paths of light rays. This can produce effects known as gravitational lensing, where light from objects behind the black hole is bent around it, sometimes forming rings or multiple images. If you could look at the sky from near a black hole, the stars would appear distorted, stretched into arcs and circles by the curvature of space. The sky would look unfamiliar, as though the universe had been gently twisted. Time, too, behaves differently near a black hole. According to general relativity, strong gravity slows the passage of time relative to distant observers. A clock near a black hole ticks more slowly than a clock far away. This effect, known as gravitational time dilation, has been measured even in the weaker gravity of Earth, using precise atomic clocks at different altitudes. Near a black hole, the effect becomes much stronger. To a distant observer, an object falling toward the event horizon appears to slow down, its light becoming redder and dimmer, never quite seeming to cross the boundary. From the falling object's own perspective, however, it crosses the horizon in a finite amount of time and continues inward. This difference in perspective is one of the most intriguing aspects of relativity. Different observers, in different gravitational conditions, can experience time in genuinely different ways, and both perspectives are equally valid within the framework of physics. Now, you might wonder how something as extreme as a black hole can form in the first place. After all, stars are enormous, but they're also supported by internal pressure, the outward push of heat and radiation produced by nuclear fusion. For most of a star's life, this outward pressure balances the inward pull of gravity, creating a stable equilibrium, but stars do not burn forever. Eventually, they exhaust their nuclear fuel. When that happens, the outward pressure decreases and gravity begins to win. In smaller stars, this collapse stops when the matter becomes dense enough to form a white dwarf. In somewhat larger stars, it can form a neutron star, an object so dense that atoms themselves are crushed, leaving a sphere composed mostly of neutrons. If the star is massive enough, however, nothing can stop the collapse. Gravity overwhelms all known forms of pressure, and the core continues shrinking until it forms a black hole. That process, the death of a massive star, is one of the primary ways black holes are created. These are known as stellar mass black holes, and they are thought to be quite common in our galaxy. Astronomers estimate that the Milky Way may contain millions of them, most of them quiet and invisible, drifting through space or orbiting companion stars. Yet stellar collapse is only one pathway. As we move forward, we'll encounter black holes that formed through entirely different mechanisms, some growing slowly over billions of years, others possibly forming in the earliest moments of the universe itself. Before we move on to those varieties, there's one more subtle but important point to consider. A black hole is defined not by what it's made of, but by its mass, its spin, and possibly its electric charge. This idea is sometimes summarized by the phrase "black holes have no hair," meaning that all the complicated details of the matter that form the black hole are lost behind the event horizon, leaving only a few measurable properties. This simplicity is part of what makes black holes so elegant from a theoretical perspective. No matter what falls in, gas, dust, stars, or even light itself, the black hole is described by just a handful of numbers. At the same time, this raises deep questions about information and the nature of reality, questions that physicists are still working to answer. But those mysteries can wait for later. For now, it's enough to appreciate that black holes, despite their reputation, are governed by clear physical principles, understandable step by step. Another comforting thought is that black holes are not eternal in the strictest sense. According to a theory proposed by Stephen Hawking, black holes can slowly lose mass by emitting a faint form of radiation, now called Hawking radiation. Over incredibly long timescales, far longer than the current age of the universe, this process could cause black holes to evaporate. For large black holes, the rate of this evaporation is so slow that it's essentially negligible on human timescales. But the idea itself is remarkable. Even the darkest objects in the universe are not entirely silent. At the quantum level, there may be a faint whisper of energy escaping over unimaginable stretches of time. When you step back and look at the full picture, a black hole is not just a cosmic curiosity. It is a natural consequence of gravity, one of the many ways matter and energy can organize themselves under the laws of physics. And perhaps that is the most reassuring perspective of all. Black holes are not violations of nature's rules. They're expressions of those rules, taken to their most extreme limits. Long before a black hole ever exists, long before gravity tightens its grip beyond any hope of escape, there is a star. Not a small, quiet star like our sun, but a giant, a star so massive that its life is destined to be both brilliant and brief. These stars begin the same way all stars do, as vast clouds of gas and dust drifting through space. Over time, gravity slowly gathers that material inward, pulling it together until the center becomes hot and dense enough for nuclear fusion to ignite. Once fusion begins, a star enters a long period of balance. Gravity pulls inward, trying to compress the star, while fusion in the core pushes outward, releasing energy and creating pressure. For millions or even billions of years, those two forces hold each other in check, and the star shines steadily into the darkness. But balance in the universe is rarely permanent. Massive stars live fast. Because they contain so much material, the pressure and temperature in their cores are far higher than in smaller stars. Fusion proceeds at an enormous rate, and fuel is consumed quickly. While a star like our Sun can shine for about 10 billion years, a star many times more massive might burn through its fuel in only a few million years, a brief life on cosmic timescales. At first, the fusion process is straightforward. Hydrogen nuclei fuse into helium, releasing energy. Later, when hydrogen in the core becomes scarce, the core contracts under gravity, heating up until helium begins to fuse into heavier elements like carbon and oxygen. In very massive stars, this process continues further. Carbon fuses into neon, neon into oxygen, oxygen into silicon, and eventually silicon into iron. Each stage happens faster than the last. The fusion of hydrogen may last millions of years, helium fusion perhaps hundreds of thousands, but by the time the core is producing iron, the timescale shrinks dramatically. That final stage may last only days. Iron is the turning point. Fusion releases energy only when lighter elements combine into heavier ones up to iron. Beyond iron, fusion consumes energy rather than releasing it. So when the core of a massive star becomes mostly iron, fusion can no longer provide the outward pressure needed to resist gravity. And gravity, patient and relentless, begins to take over. What follows is one of the most dramatic events in the universe, though from far away it unfolds in near silence. The core of the star collapses, not slowly but in a matter of seconds. The inward pull of gravity becomes overwhelming, and the material in the core falls inward at tremendous speeds. To understand how sudden this collapse is, imagine a sphere larger than Earth, compressing to a much smaller size in less than a minute. The densities and temperatures rise beyond anything we can easily picture. Atoms are crushed. Electrons and protons are forced together, forming neutrons and releasing vast numbers of neutrinos, tiny particles that pass through matter almost effortlessly. In some cases, this collapse halts when the core becomes a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. But if the original star is massive enough, even neutron degeneracy pressure, the force that resists further compression, cannot stop the collapse. Gravity continues to win. The core shrinks further, and once it is compressed within a critical radius, the escape velocity exceeds the speed of light. At that moment, a black hole is born. Interestingly, the formation of the black hole itself is hidden from view. The event horizon forms deep within the collapsing core, and from the outside we cannot see the exact instant it appears. What we do see is something else, something far more visible. The outer layers of the star reacting to the collapse of the core. When the core suddenly shrinks, it creates a shock wave that travels outward through the star. Combined with the flood of neutrinos released during collapse, this shock can blow the outer layers of the star into space in an enormous explosion known as a supernova. For a brief time, that single dying star can outshine an entire galaxy. These explosions scatter heavy elements into space, elements like gold, uranium, and many of the atoms that make up planets and living things. It's a curious thought that the material in our own bodies was forged in ancient stars and dispersed by explosions like these. The death of massive stars is not only destructive, it is also creative, seeding the galaxy with the ingredients for new stars, new planets, and eventually new forms of life. At the center of that expanding cloud of debris, the black hole remains, silent and dark, a remnant of the star that once shone. Not every massive star produces a spectacular supernova. In some cases, the collapse may happen so completely that much of the star falls inward rather than being blown outward. Astronomers sometimes call these failed supernovae, events where a massive star simply fades from view, leaving behind a black hole with little outward drama. Imagine a star visible in the night sky one year, and then, over the course of months, it dims and disappears, leaving nothing behind that can be seen with ordinary telescopes. Only careful measurements of the surrounding region might reveal the presence of a newly formed black hole. There is something almost eerie about that possibility, a reminder that not all cosmic events announce themselves with brilliant fireworks. Some endings are quiet. The mass of the original star determines the kind of remnant that forms. Stars several times the mass of the Sun may leave neutron stars, while those more than roughly 20 times the Sun's mass are more likely to produce black holes, though the exact threshold depends on many details, including the star's composition and rotation. Rotation, in fact, plays an important role. Stars are rarely perfectly still. Most rotate, some quite rapidly, and as a star collapses, its rotation speeds up, much like an ice skater pulling in their arms. This conservation of angular momentum can cause the forming black hole to spin, and that spin affects the behavior of space and matter around it. A rotating black hole drags space itself around with it, a phenomenon known as frame dragging. But we'll explore spinning black holes in more detail later because they form an important category of their own. Another factor that influences black hole formation is the presence of a companion star. Many stars exist in binary systems orbiting a partner. When one star in such a system collapses into a black hole, the story doesn't necessarily end there. The black hole may begin pulling material from its companion, forming a glowing disk of gas that spirals inward and heats up to extraordinary temperatures. These systems, known as X-ray binaries, are among the ways astronomers first confirm the existence of stellar mass black holes. The black hole itself remains invisible, but the hot gas around it shines brightly in X-rays, revealing the presence of something compact and massive. It's fascinating to consider that many black holes in our galaxy may have formed billions of years ago and have been drifting through space ever since, mostly unnoticed. The Milky Way could contain millions of them, scattered quietly among the stars. And yet, despite their abundance, black holes formed from stellar collapse are only the beginning of the story. The universe contains black holes of many sizes and origins, some far larger than anything a single star could produce. Before we move on to those, it's worth lingering a little longer on the process of collapse itself, because it reveals something profound about the nature of gravity. Gravity is often described as the weakest of the fundamental forces, and in many ways that's true. A small refrigerator magnet can easily overcome the gravitational pull of the entire Earth on a paperclip. But gravity has one unique property. It always attracts, never repels, and because of that, its effects accumulate. Over time, gravity gathers matter, building larger and larger structures, clouds, stars, galaxies. And in the most extreme cases, gravity gathers so much matter into such a small space that it creates a black hole. There's a kind of inevitability in that process. Once a sufficiently massive core begins to collapse, and no known force can halt it, the formation of a black hole becomes unavoidable, a natural consequence of the laws of physics. It's also interesting to reflect on how brief the actual birth of a black hole is compared to the long life of the star that precedes it. A massive star may shine for millions of years, but the collapse of its core happens in seconds. An entire lifetime ends in an instant, and a new kind of object begins to exist, one that may persist for trillions of years or more. Time itself behaves differently near black holes, as we discussed earlier, but even without considering relativity, the contrast in timescales is striking. Long, slow beginnings followed by sudden dramatic endings. Astronomers continue to study supernovae and stellar collapses in order to understand these processes better. Modern telescopes can detect neutrinos from nearby supernovae, measure the gravitational waves produced when massive objects collide, and observe the remnants left behind. Each observation adds another piece to the puzzle, helping us understand not only how black holes form, but how stars live and die, how galaxies evolve, and how the elements essential to life are distributed throughout the universe. The universe is vast and sometimes violent, but it is also consistent. The same physical laws apply everywhere, from the smallest particles to the largest galaxies. Black holes are not exceptions to those laws. They are among their most striking consequences. So when we look up at the night sky and see the faint glow of distant stars, it's worth remembering that some of those stars are already gone, their light still travelling toward us across years or centuries of space. Somewhere out there, unseen black holes mark the places where brilliant suns once burned. Once a massive star has lived its brief, brilliant life and gravity finally overwhelms the forces holding it up. What remains is often a black hole that is, by cosmic standards, relatively modest in size. These are known as stellar mass black holes, and although the name may sound technical, it simply means black holes formed from individual stars. They are the most common type of black hole in the universe, and in many ways they are the easiest to understand, because their origins are closely tied to processes astronomers have studied for decades: the birth, life, and death of stars. A typical stellar mass black hole contains anywhere from about 3 times the mass of our Sun to perhaps a few dozen times that amount. That might sound enormous, and it certainly is when compared to planets or moons, but in the scale of galaxies it is quite small. The black hole at the centre of the Milky Way, for example, has a mass of about 4 million suns, far larger than anything produced by the collapse of a single star. Yet despite their smaller size, stellar mass black holes are remarkable objects. What makes them especially fascinating is the contrast between their mass and their physical size. A black hole with 10 times the Sun's mass might have an event horizon, only about 30 kilometers across, roughly the size of a city. Imagine compressing something heavier than 10 suns into a region smaller than a metropolitan area. The density involved is almost beyond comprehension, and still, from a safe distance, such a black hole would not appear dramatic or frightening. It would not glow or roar. Unless it were actively pulling in material, it would simply sit in darkness, detectable only through its gravitational influence. For a long time, this made stellar mass black holes very difficult to find. Astronomers cannot see black holes directly, because they emit no light. Instead, they must look for clues, subtle hints that something massive and invisible is present. One of the earliest and most important clues came from binary star systems. Many stars exist in pairs, orbiting a common centre of gravity. In some cases, one of those stars evolves more quickly, becoming a red giant, exploding as a supernova, and leaving behind a compact remnant. If that remnant is a black hole, the system may continue to exist, with the black hole orbiting its companion star. And here, something interesting can happen. If the two objects are close enough, the black hole's gravity can begin pulling gas away from the companion star. That gas doesn't fall straight in. Instead, it forms a swirling disk called an accretion disk, heating up as friction and compression increase its temperature. By the time the gas spirals close to the event horizon, it can reach temperatures of millions of degrees, hot enough to emit intense X-rays. These X-rays can be detected by telescopes in orbit around Earth, revealing the presence of an invisible but powerful object. One of the first strong candidates discovered this way was Cygnus X1, an X-ray source in the constellation Cygnus. Observations showed that a visible star in that system was orbiting an unseen companion with a mass far too large to be a neutron star. The most plausible explanation was a black hole, and over time additional evidence confirmed it. Discoveries like this gradually changed black holes from theoretical curiosities into real, observable objects. Today, astronomers have identified many stellar mass black holes in our galaxy, and they suspect there are millions more that remain undetected, either because they are not actively accreting matter or because they are too distant to observe clearly. It's interesting to think about how quiet most of these objects must be. A black hole drifting alone through interstellar space would be almost impossible to detect. It would pass through the galaxy silently, influencing only the occasional grain of dust or stray particle of gas. Sometimes, however, stellar mass black holes reveal themselves in another way, through gravitational waves. When two black holes orbit each other in a binary system, they gradually lose energy by emitting ripples in space-time itself. These ripples, predicted by Einstein's theory of general relativity, travel outward at the speed of light, stretching and compressing space by tiny amounts. In 2015, scientists made the first direct detection of gravitational waves using the LIGO observatories. The signal came from the merger of two stellar mass black holes more than 1 billion light-years away. For a brief moment, the energy released in gravitational waves exceeded the total energy output of all the stars in the observable universe combined, though by the time the waves reached Earth the effect was extraordinarily subtle, changing distances by less than the width of a proton. That detection opened a new way of observing the universe, one that doesn't rely on light at all. Since then, many more black hole mergers have been observed, revealing populations of stellar mass black holes that would otherwise remain hidden. Another intriguing aspect of stellar mass black holes is how diverse they can be. Not all massive stars are identical, and the details of a star's mass, composition, rotation, and environment all influence the black hole that forms. Some black holes spin rapidly, dragging space-time around them in a phenomenon known as frame dragging. Others may rotate more slowly. The spin affects how matter behaves near the event horizon, shaping the structure of accretion disks and the powerful jets that some black holes produce. Those jets are among the most dramatic features associated with black holes. In certain systems, magnetic fields in the accretion disk can channel some of the infalling material into narrow beams that shoot outward at nearly the speed of light, extending for vast distances into space. These jets can influence the surrounding interstellar medium, compressing gas clouds and sometimes even triggering the formation of new stars. So even relatively small black holes can have effects far beyond their immediate surroundings. It's also worth considering how many stellar mass black holes may exist in our own galaxy. The Milky Way contains hundreds of billions of stars, and a significant fraction of those stars are massive enough to end their lives in core collapse supernovae. Not all of those collapses produce black holes, but many do. Estimates suggest that the Milky Way may contain tens of millions of stellar mass black holes. Most of them are invisible, wandering through the galaxy in darkness, relics of stars that lived and died long before the sun was born. Every once in a while, astronomers detect one passing in front of a distant star, producing a phenomenon called gravitational microlensing. The black hole's gravity bends the light from the background star, causing it to brighten temporarily. By carefully analysing these events, scientists can infer the presence of objects that emit no light at all. There is something quietly profound about this. Entire populations of objects, completely invisible, revealed only through the bending of starlight or the faint whisper of gravitational waves. Stellar mass black holes also help astronomers understand the lives of stars. By studying the masses and spins of black holes detected through gravitational waves, scientists can learn about the stars that formed them, the environments in which those stars lived, and the processes that led to their collapse. For example, some black holes detected in mergers have been unexpectedly massive, suggesting that they formed from stars in regions with very low concentrations of heavy elements. In such environments, stars lose less mass through stellar winds, allowing them to retain more material until the moment of collapse. In this way, black holes become records of cosmic history, preserving information about conditions in distant galaxies and earlier eras of the universe. Another gentle reminder emerges here as well. Despite their dramatic reputation, stellar mass black holes are not dangerous unless you are very close to one. The nearest known black hole is thousands of light years away, and even if one were closer, space is so vast that encounters are extraordinarily unlikely. Gravity weakens rapidly with distance, and beyond a certain range, a black hole's influence is no different from that of any other object with the same mass. The idea of black holes roaming the galaxy, swallowing stars at random, belongs more to fiction than to astrophysics. Most of the time, the universe is a quiet place, and stellar mass black holes are part of that quietness. Most scientists believe that a full theory of quantum gravity, one that unifies general relativity with quantum mechanics, will eventually provide a more accurate description of what happens in these extreme environments. But for now, the singularity remains a boundary of understanding. There is something quietly humbling about that. After centuries of scientific progress, there are still places in the universe where our knowledge reaches its limits. Another fascinating aspect of black hole interiors involves the nature of time and space. Outside a black hole, we're used to thinking of time as something separate from space, a dimension that moves steadily forward. Inside the event horizon, the roles of space and time begin to change in ways that are difficult to visualize. In a sense, the singularity lies in the future of anything that crosses the horizon. Just as we cannot avoid moving into the future, an object inside a black hole cannot avoid moving toward the singularity. It is not merely falling through space, it is moving through space-time in a direction that inevitably leads inward. This idea can feel abstract, but it reflects the deep connection between space and time in Einstein's theory. Gravity does not simply pull objects through space, it reshapes the geometry of space-time itself, altering the directions that motion can take. There are also theoretical possibilities, still debated and explored, about what might exist inside black holes beyond the classical picture. Some solutions to Einstein's equations suggest the existence of wormholes, hypothetical tunnels connecting distant regions of space-time. Others propose that quantum effects might prevent the formation of true singularities, replacing them with extremely dense but finite structures. These ideas remain speculative, but they illustrate how black holes continue to challenge and expand our understanding of physics. Another deep question concerns information. When matter falls into a black hole, it carries information about its structure, composition, and quantum state. According to classical general relativity, that information disappears behind the event horizon, seemingly lost forever. But quantum mechanics suggests that information cannot be destroyed. This conflict, known as the black hole information paradox, has been one of the central puzzles in theoretical physics for decades. Stephen Hawking's discovery that black holes emit radiation added a new layer to this puzzle. If black holes can evaporate over time, what happens to the information contained in the matter that fell into them? Does it escape in some subtle form? Is it preserved on the event horizon? Or does it remain in some hidden way that we do not yet understand? Many proposed solutions exist, involving ideas such as holographic principles, where information about a volume of space is encoded on its boundary, or the possibility that correlations in Hawking radiation carry information outward. These are complex and ongoing areas of research, but they highlight how black holes sit at the intersection of some of the deepest questions in physics. It's also interesting to reflect on how different observers perceive events near the event horizon. To someone falling in, the crossing happens in a finite time, and the journey inward continues. To a distant observer, the infalling object appears to slow down, fade, and never quite cross the horizon. Both perspectives are valid within the framework of relativity, even though they seem to contradict each other. This duality is one of the many ways black holes challenge our everyday intuition. There is also the question of whether anything could survive inside a black hole, even briefly. The answer depends on the size of the black hole and the nature of the object falling in. Near a supermassive black hole, tidal forces at the horizon may be mild enough that a spacecraft could cross without immediate destruction. But deeper inside, the increasing curvature of space-time would eventually tear apart any known form of matter. Even light cannot escape, but light still exists inside, travelling along paths that lead inevitably inward. The interior of a black hole is not empty. It contains whatever matter and radiation have fallen in, compressed and transformed in ways we cannot yet fully describe. Some physicists have speculated about the possibility that black holes might contain entire regions of space-time, perhaps even new universes, hidden from our own. These ideas are highly speculative, but they arise naturally from certain solutions of the equations of general relativity. Whether they have any connection to reality remains unknown. What is certain is that black holes represent the most extreme environments known, places where gravity, quantum mechanics, and thermodynamics all play crucial roles. They are not merely exotic objects, but keys to understanding the fundamental nature of the universe. There is something quietly profound about that. Objects once considered purely theoretical, once thought too strange to exist, are now observed and studied, guiding us toward deeper insights about space, time, and reality itself. And yet, even with all we have learned, the interior of a black hole remains in many ways beyond our reach. It is a reminder that science is not only about answers but also about questions, about exploring the edges of knowledge and gradually pushing them outward. Perhaps future theories will reveal what truly happens at the singularity, or whether singularities exist at all. Perhaps new observations will uncover phenomena we have not yet imagined. The story is still unfolding, and the universe still has much to teach us. As our exploration continues, it becomes clear that black holes are not isolated curiosities but part of a broader cosmic pattern. They form, evolve, merge, and influence their surroundings, playing a role in shaping galaxies and the large-scale structure of the universe itself. After exploring so many different kinds of black holes, from the remnants of dying stars to giants weighing billions of suns, from hypothetical microscopic ones to ancient objects that may have formed near the beginning of time, a quiet question naturally begins to form. Why are there so many kinds of black holes at all? At first it might seem as if there should be only one type. After all, a black hole is defined by a simple condition: enough mass compressed into a small enough space that not even light can escape. The idea itself is straightforward, and yet when we look closely at the universe, we find an entire spectrum of black holes, each shaped by different origins, environments, and histories. The reason for this diversity lies in something both simple and profound. The universe itself is diverse. Stars are born with different masses, rotate at different speeds, and live in different surroundings. Galaxies collide, clusters evolve, and gas flows in complex patterns across cosmic time. Gravity acts everywhere, but it acts on matter that is never perfectly uniform. Small differences at the beginning lead to large differences over billions of years. Black holes, in this sense, are not exceptions to the universe's variety. They are products of it. Consider stellar mass black holes. These form when massive stars reach the ends of their lives and collapse under their own gravity. the mass of the original star, the rate at which it rotated, the presence or absence of a companion, and the composition of the surrounding gas all influence the black hole that remains. Some are heavier, some lighter, some spin rapidly, others more slowly. Move outward in scale, and intermediate mass black holes may form through repeated mergers in dense clusters, or from the collapse of unusually massive stars in the early universe. The pathways differ, but the underlying process is still gravity gathering matter over time. At the centers of galaxies, supermassive black holes grow through accretion and mergers, shaped by the histories of their host galaxies. Galaxies that collide frequently may produce larger central black holes. Galaxies with abundant gas may feed their black holes more efficiently. Over billions of years, these differences accumulate, producing the wide range of masses we observe. Ultramassive black holes represent the most extreme outcomes of these processes, objects that grew for immense stretches of time, sometimes in environments rich in gas, sometimes through repeated mergers in crowded clusters of galaxies. Then there are primordial black holes, if they exist, which would represent an entirely different origin story. Not the death of stars or the growth of galaxies, but the collapse of dense regions in the earliest moments of cosmic history. These would be relics of the young universe itself, shaped by conditions that no longer exist today. Even micro-black holes, though hypothetical, arise naturally from the same physical laws when applied at very small scales. They remind us that the equations of gravity do not care about size. They apply equally to the very large and the very small. And beyond size and origin, there are other ways black holes can differ. Some spin rapidly, dragging space-time around them. Some may carry tiny amounts of electric charge. Some exist in pairs, spiraling together over millions of years, while others drift alone through interstellar space, silent and solitary. All of this variety emerges from the same underlying principles: gravity, motion, and the passage of time. There is something deeply reassuring about that. The universe does not need special rules to produce extraordinary phenomena. The same laws that cause an apple to fall or the moon to orbit Earth also produce quasars, gravitational waves, and the shadows of black holes in distant galaxies. Complexity arises naturally when simple rules operate over vast scales. Black holes also reveal something important about the history of the universe. Each one carries, in a sense, a record of the processes that formed it. The mass of a black hole tells us about the matter that collapsed or merged. Its spin carries clues about past accretion or collisions. Its environment reveals the conditions of the galaxy or cluster in which it resides. By studying black holes, astronomers are not just learning about these objects themselves. They are learning about stars, galaxies, and the evolution of the cosmos. For example, the existence of supermassive black holes in nearly every large galaxy suggests that black hole growth and galaxy formation are closely linked. The discovery of ancient quasars tells us that massive structures formed earlier than once expected. Observations of gravitational waves reveal how often black holes merge and how common different types of stellar remnants are. Each new piece of data adds to a larger picture, a picture of a universe that is dynamic, evolving, and interconnected. Another lesson from black holes concerns the nature of space and time. These objects show us that space-time is not rigid but flexible, shaped by mass and energy. They demonstrate that time can slow, that light can bend, and that the geometry of the universe can become so curved that entire regions are cut off from the rest. These are not merely curiosities, they're clues about the fundamental structure of reality. Black holes also bring together some of the deepest areas of physics. General relativity describes their large-scale behavior, while quantum mechanics becomes important near their horizons and in the process of Hawking radiation. Thermodynamics appears in the form of black hole temperature and entropy. Few other phenomena connect so many branches of science in such a direct way. It is possible that understanding black holes more fully will lead to breakthroughs in our understanding of gravity, quantum theory, and the origin of the universe itself. There is also a more reflective way to think about this diversity. The universe is not uniform or repetitive. It is creative, in the sense that simple laws produce an astonishing range of structures and phenomena. Stars differ, planets differ, galaxies differ, and black holes differ. Variety is not an exception. It is the natural outcome of time and complexity. When we look up at the night sky, we see points of light that appear calm and unchanging, but behind that stillness lies a history of formation, collapse, collision, and transformation. Black holes are part of that history, silent witnesses to the lives and deaths of stars, the merging of galaxies, and the slow unfolding of cosmic time. It is also worth remembering that our understanding of black holes is still evolving. Only a few decades ago, their existence was uncertain. Today we can detect their mergers, measure their spins, and even image the glowing matter at the edge of their event horizons. Future observations will almost certainly reveal new kinds of black holes, new behaviors, and new connections to other areas of physics. The story is far from complete, and perhaps that is the most comforting thought to carry with you. The universe is not a finished book, but an unfolding one. There are still discoveries to be made, still questions to be asked, still mysteries waiting quietly in the darkness. Somewhere out there, black holes of many kinds are forming, merging, drifting, and slowly evolving. Part of a cosmos that is vast, patient, and endlessly fascinating. And as we continue to explore and to listen, to observe and to wonder, we become part of that story too, participants in a long tradition of curiosity that stretches from the first stargazers to the astronomers of today, and onward into a future where the quiet secrets of the universe will keep revealing themselves, one gentle discovery at a time.